We like to think of the universe as endless, an infinite expanse of galaxies, a boundless sea of stars stretching forever in every direction, a cosmic canvas too vast to chart. It comforts us, this idea of an eternal frontier, as if discovery will always be possible, as if the answers are just waiting somewhere out there. But what if that's not true? What if, instead of an infinite playground, the universe is more like a walled garden, expanding, yes, but hemmed in by invisible boundaries we're only beginning to glimpse? Not poetic barriers, but hard physical limits woven into the very structure of space, time, and information. Limits that don't just stop our eyes, but halt our equations, break our simulations, and erase the very data we seek. This isn't simply a matter of how far our telescopes can see. It's about the point where observation ends and certainty dissolves, the moment when even light runs out of road. We're not just facing the edge of the universe, we're approaching the edge of understanding, and it's far closer than anyone imagined. A universe with walls rethinking infinity. We thought the universe went on forever for hundreds of years, a huge area that goes on forever and in all directions. For one thing, when you look up at night, the stars seem to go on forever, a sparkling sea of light that goes everywhere. The infinite was talked about by philosophers. It was idealized by poets, and cosmologists, even the most skeptical ones, often treated the cosmos as effectively infinite in both size and potential. But what if that assumption is wrong? What if the universe is not infinite, and the edges, though distant, are real and measurable? More provocatively, what if we've already reached them? This might sound like science fiction, but it's a question grounded in hard science. Modern physics is increasingly confronting the idea that there are limits to what we can know, limits to what we can observe, and perhaps even limits to what exists. Not metaphorical limits. Actual, structural boundaries built into the fabric of space, time, and information itself. Take the speed of light, not just a fast thing, but the fastest thing. It's a built-in speed limit on how fast information can travel. That means even if the universe were infinite, we wouldn't know it. Light can only travel so far in a given amount of time. And since the universe is about 13.8 billion years old, there's a hard cutoff on what we can observe. Beyond a certain distance, we simply can't see anything, because the light from those places hasn't had enough time to reach us yet. Scientists call this the observable universe, which is a sphere 93 billion light-years across that goes around Earth. That is farther than 13.8 billion light-years because the universe has been growing while the light has been moving. Do not be fooled, though. The world we can see is very big, but that does not mean it's endless. The visible limit is actually a hard limit in real life. After that, darkness. Not because there is nothing there, but because we can't get to it. And that's just the beginning. When we dig into the details, we find even more constraints, like cosmic horizons that grow smaller over time, quantum uncertainties that wall off our knowledge at the smallest scales, and energy limits that cap how much data the universe can physically hold. It's like trying to play an open-world video game, only to realize that behind the mountains in the distance, there's just an invisible wall. The universe might be a lot more like that than we'd like to believe. The speed of light, nature's hard ceiling. The speed of light is 299,792,458 meters per second, which may not seem like much at first. However, this number isn't made up, and it's not just very fast. It is the most basic limit in the whole world. No matter how crazy the science fiction spaceship or particle is, it can't be topped. It's not just speed, it's a wall. Why? Because the speed of light isn't merely about motion, it's woven into the very fabric of space and time. Einstein's theory of relativity showed us that as something accelerates toward the speed of light, time slows down for it. Push further, and something stranger happens. Time practically stops, and mass approaches infinity. To actually reach the speed of light, you'd need infinite energy. That's not just impractical, it's impossible. This limitation defines what we can know and when we can know it. Light carries information. It's how we see, how we measure distance, how we study galaxies, stars, and cosmic microwave background radiation. Everything we know about the universe outside our own planet, we know it because light brought that information to us. But light takes time. When we look at the sun, we're seeing it as it was 8 minutes ago. When we gaze at the Andromeda galaxy, we're seeing it as it was 2.5 million years ago. The farther we look, the deeper we're peering into the past, not because of some trick, but because that's how long it took the light to travel. There are regions of space whose light will never reach us. Not eventually, not in a million years. Never. Why? Because the universe is expanding, and that expansion is accelerating due to dark energy. As space stretches, distant galaxies are being pulled away from us faster than light can keep up. Their light is essentially running on a treadmill that's speeding up faster than they can advance. That means some parts of the universe are permanently slipping out of reach. This is the origin of the cosmic event horizon, a boundary beyond which events can never affect us. Not now, not ever. Those galaxies are, for all practical purposes, gone. We will never know what happens to them, no matter how powerful our telescopes become. And this changes how we understand time itself. In a universe that had no speed limit, we might imagine exploring every star, scanning every corner, waiting long enough for every signal to arrive. But the speed of light cancels that fantasy. There's a maximum pace at which reality can unfold, and it's already cutting us off from vast portions of the cosmos. The cosmic horizon, where observation ends. Image yourself standing on the edge of a very large ocean. It seems like the waves go on forever, but you know there's a place beyond which you can't see. Not because the ocean stops, but because you can't see any further. That's how the universe really works. We live on a small island that can be seen in the middle of an ocean of space that we don't understand. And where is the edge of that sight? The cosmic boundary is the name for it. Also known as the observable universe, this horizon is the farthest edge of what we can detect, the ultimate limit of what light has had time to reach us since the birth of the cosmos. But here's the twist. It's not just a question of distance, it's a question of time. The universe is approximately 13.8 billion years old, which means that's how long light has had to travel. But because space itself expands, the actual radius of the observable universe is much larger, about 46.5 billion light-years in every direction. This paradoxical effect is the result of cosmic expansion. Even as light races toward us, the space it travels through is stretching. It's like running up an escalator that's moving in the opposite direction, and that escalator is speeding up. So, while light might have only had 13.8 billion years to journey across space, the expansion has pulled its source much farther away than that. And so, our cosmic horizon is set not by a wall, but by time and motion conspiring together. Inside this boundary, we can see galaxies, quasars, nebulae, light from the earliest stars, even the faint afterglow of the Big Bang itself. But beyond it, there's silence. Not because there's nothing there, but because we simply cannot see it. Those regions are too far, the light hasn't had time to arrive, and because of the universe's accelerating expansion, it never will. This has very important scientific implications. In the real world, there are limits to what we can check, watch, and test. In any real way, we can't know what's beyond the cosmic limit. Scientists can still make guesses, but no observation will ever prove or disprove those guesses, unless something very basic about the world changes. That horizon is shrinking, relatively speaking. As expansion continues to accelerate due to dark energy, more and more galaxies are redshifting out of view. That means every year, our observable universe actually contains less. More galaxies fall off the radar. More events become permanently unobservable. In the far future, only the local group of galaxies, the Milky Way, Andromeda, and a few dozen small ones will remain visible. Everything else will be gone, not destroyed, just unreachable, like ghosts behind a one-way mirror. We often speak about science as a process of revealing, uncovering, exposing what was hidden. But in cosmology, there's another side to the story. Every discovery comes with a closing door. Every measurement reminds us of the vastness we cannot reach. Redshift and the fading of the distant universe. Light is more than just light. It's information. Every photon that comes to us from space has a message on it. It has a timestamp, a temperature, and a mark of the past. But as space expands, it changes light, just like it changes everything else in the world. And that growth leaves a mark. Wavelengths get longer, which is called redshift. To understand redshift, imagine a moving ambulance. As it approaches, the siren sounds higher. As it moves away, it drops to a lower pitch. This is the Doppler effect, and light does something similar. When galaxies move away from us, the light they emit gets stretched into longer, redder wavelengths. But this isn't just about motion, it's about the stretching of space itself. It pulls light along with it as the universe grows. A photon that started its trip in the blue light of a young star billions of years ago might look red or even infrared when it gets to Earth, because it has been stretched by the universe itself on its way. Space has had more time to stretch the wave the farther away it is from the source. Plus, there is some light that is stretched so much that it leaves the visible range and can't be seen by even the most sensitive devices. This redshift isn't a subtle effect. It's a cosmic censorship mechanism. Objects beyond a certain distance become so redshifted that they effectively fade from view. Not because they stopped shining, but because their light has been stretched into oblivion. Astronomers categorize this using a value called Z, the redshift factor. The higher the Z, the older and farther away the source. We currently observe galaxies with redshifts over Z equals sign 10, meaning their light has been stretched more than tenfold. But eventually, redshift reaches a tipping point. Past a certain threshold, galaxies not only dim, they disappear. Their photons are redshifted into wavelengths we cannot detect. Even if we had perfect telescopes, their light would be so diluted across time and space that it might as well not exist. Visualize this happening on a cosmic level. This redshift horizon is crossed by more galaxies every year. They don't explode or blink out. Instead, they fade away because the speed of the universe's growth is faster than their photons. Sky isn't always there. The light is slowly going out, like fire coals going out. In the far future, space will appear darker, emptier. New civilizations might look up and see only the handful of galaxies bound to their local group, unaware that billions more once existed, lost not to time, but to redshift. Redshift means data is vanishing. Information is leaking beyond the horizon of detectability. The deeper we try to peer into space, the more we run up against this stretched and fading wall. At some point, we stop seeing the universe as it was and start bumping into the edge of what's possible to know. And it's not just the far-off galaxies that are disappearing. It's their stories, their pasts, their secrets. The universe is pulling away from us. And no amount of curiosity, no lens or telescope can change that. The cosmic microwave background, our oldest snapshot. What we call the cosmic microwave background, CMB, shows that moment. It is the oldest light in the universe and one of the most important science artifacts we have found. You can't see it with your eyes. It's just a soft glow in the microwave range of the spectrum that has been stretched out over billions of years as the universe has grown. What was a fireball is now just a whisper. Roughly 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen. This process, known as recombination, suddenly allowed light to travel unimpeded for the first time. The fog lifted. And that first light has been racing outward ever since, like a message in a bottle from the infancy of space-time. The CMB is our cosmic photograph of that moment, a 2D snapshot of a 3D universe frozen in time. And remarkably, it looks almost perfectly uniform in every direction, but not quite. There are tiny temperature fluctuations, differences of 1 part in 100,000, that represent the seeds of structure, the birthplaces of galaxies, clusters, and everything we see today. These variations in temperature and density are crucial. They're evidence that quantum fluctuations in the early universe were stretched to cosmic scales by inflation, setting the stage for the large-scale structure of the cosmos. Without the CMB, we'd have no clue how the raw material of the universe turned into galaxies, stars, and planets. But this is where the CMB shows us the first hard limit on what we know. Not only is it the oldest light we can see, but it's also the farthest. When the CMB came out, everything that happened before it was hidden behind a veil. In normal light, the universe before 380,000 years ago can't be seen. We can figure it out. We can make a copy of it, but we can't see it because photons from that time haven't reached us yet. That makes the CMB our cosmic event horizon in the electromagnetic sense. It's the edge of the visible cosmos, not because there's nothing beyond it, but because we have no way to see beyond it using light. It's a wall made not of matter, but of physical limitation. What's more, as the universe continues to expand, this background light will continue to redshift, becoming fainter and more stretched with each passing epoch. In the distant future, even the CMB will be undetectable, too cold and faint for any observer to measure. Future astronomers may never even know it existed. So when we look into the CMB now, we're not just seeing the past, we're seeing a window that goes away. A quick, bright look into a cosmic dawn that we'll never fully grasp. We can touch every pixel in that old glow, but we can never go past it. Hubble's Law, the expanding universe, reveals its edge. In 1929, Edwin Hubble changed the course of cosmology forever, not by peering into the vastness of the universe and discovering what was there, but by noticing what it was doing. He realized that every distant galaxy wasn't just drifting through space, it was racing away. And the farther it was, the faster it fled. This observation became known as Hubble's Law. The velocity at which a galaxy recedes is directly proportional to its distance from us. In simple terms, space itself is expanding. And that revelation doesn't just tell us how galaxies behave, it defines the limits of the observable universe. Unlike an explosion, which sends pieces into space from where there wasn't any before, the Big Bang didn't happen in space. It made space, and as space grows, galaxies move farther apart. In other words, the farther away you look, the longer the time has passed since the light was given off. And galaxies move farther away than the speed of light when they're far enough away. This isn't because they're going through space, but because space is expanding beneath them. This leads to a very important thought. There are galaxies we will never see, at any time, no matter how long we have to wait. There is light coming from those galaxies toward us, but the space between us is growing faster than the light can go through it. It's like trying to race up an elevator that goes up faster than you can go down. The current estimate for the observable universe is about 93 billion light-years across, even though the universe itself is only 13.8 billion years old. That's because, while the light was traveling, space expanded. And beyond that distance, galaxies vanish, not because they cease to exist, but because their light never reaches us. They're beyond the cosmic horizon. This expansion also has an important consequence for the fate of information. As galaxies move beyond our reach, their light becomes so redshifted, so faint, that they effectively disappear from our view. A few 100 billion years from now, only our local group of galaxies will remain visible. Everything else will have faded beyond detection. To future observers, the universe will seem dark, static, and empty. Hubble's law does a trick in the universe. It lets us see what's right in front of us while removing everything beyond it. More galaxies cross the imaginary line every year. More and more information is lost every second. We might not remember they were there if we don't look now. The last surprise is that the rate of growth isn't slowing down. Thanks to dark energy, it's speeding up. In other words, the cosmic horizon is getting smaller, not bigger. Not only is the world big, it's also trying to hide from us. The invention of the invisible, tools that let us see the unseeable. For most of human history, our genetics made it hard for us to understand the world. We only knew what our eyes could see and what we could feel. The seasons were marked by the stars that flew above us. Our senses give us a small window through which to see and understand the world and the universe beyond it. Then, something revolutionary happened. We began to invent tools to see the unseeable. The telescope, invented in the early 17th century, extended our gaze across the heavens. Suddenly, the planets weren't just lights in the sky. They were worlds. The microscope turned the invisible small into a visible reality, revealing a universe teeming with life in a single drop of water. These devices didn't just enhance our perception, they transformed it. They rewrote our understanding of what existed. And as centuries passed, the inventions multiplied. Spectrometers to analyze the fingerprints of light, X-ray detectors to peer into cosmic gas clouds, radio arrays to catch whispers from dying stars. Particles collide to smash matter into its primordial parts. Gravitational wave detectors to let us hear, not just see, the collisions of massive objects in the dark. Each of these tools pulled back a curtain. Each revealed a new layer of the universe that had been there all along, just waiting for us to invent a way to see it. No matter how advanced our telescopes become, there will always be a distance beyond which photons cannot reach. No matter how sensitive our detectors are, some gravitational waves will be lost to cosmic noise. No matter how powerful our colliders, we'll never probe below the Planck length. And no matter how fast our processors, there will always be data we can't store or decode. The tools we build are physical, bound by material, power, and entropy. But even their theoretical successors, imagined in thought experiments or futuristic speculation, run up against fundamental limits. Limits set not by human shortcoming, but by the architecture of reality itself. Take the James Webb Space Telescope. It's the most sensitive infrared observatory ever built. But it cannot see beyond the cosmic microwave background, because light simply didn't exist in the universe before a certain time. Even perfect instruments cannot measure what physics says is unknowable. Or consider gravitational wave detectors like LIGO and Virgo. They can catch the shudders of space-time from black hole collisions millions of light-years away. But beyond a certain redshift, even these ripples fade to undetectable silence. We've only just opened a new sense, but that sense, too, has boundaries. Even the most innovative ideas we come up with are asymptotic. They bring us closer to the unknown, but they never get past the last obstacle. There are bigger antennas, more powerful colliders, and better instruments that we make. The darkness still wins. Tools are what we do. It's in our genes. We will keep making things like neutrino observatories, quantum devices, and AI-powered modeling engines. But gravity, energy, and chance are so strong that even the smartest tools can't break through them. The observable versus the entire universe. The illusion of seeing it all. It's easy to think that when we look up at the stars at night or through the James Webb Space Telescope, we can see everything that the world has to offer. There are galaxies, stars, quasars, and the cosmic microwave background. It all seems perfect. On the other hand, this view is both comfortable and completely false. What we call the observable universe is defined by a simple rule: how far light has traveled since the universe began. Given that the cosmos is around 13.8 billion years old, you might think the observable universe extends about 13.8 billion light-years in all directions. But that's not the case, because the universe has been expanding the whole time. Light from very distant sources has had to chase a moving target. As a result, the actual radius of the observable universe is around 46.5 billion light-years, meaning the full diameter is about 93 billion light-years across. And here's where things get mind-bending. According to many models of inflation and cosmic expansion, the universe may not just be big, it may be infinite, or at the very least much larger than we could ever probe. And that means what we see through telescopes, The entirety of the visible cosmos might be like a single pixel on an endless screen. This creates a tension between cosmic humility and observational hubris. We use the observable universe to construct theories about the whole thing. We measure the curvature of space, the abundance of elements, the distribution of galaxies, and then we extrapolate. We say, the universe is flat, or it contains 5% ordinary matter, 27% dark matter, and 68% dark energy. But we're basing that on a volume that may be a speck compared to the real thing. Another thing that means the world beyond our view is not unique. Our patch of sky is not the only one like it. In a universe that goes on forever, every possible arrangement of matter has to happen somewhere. There might be another Earth out there, another you, and not just once, but an endless number of times, set up in every possible way. There are worlds where the rules of physics are different. A few places where galaxies never formed. There are places where black holes rule and places where they never were. All of this is still just a guess, though. We can't see past our cosmic limit, that's why. We are stuck in a box made by the speed of light and the age of space itself, even if the universe has an end. We can't pull that screen back with any new ideas, inventions, telescopes, or theories we come up with. This is a hard limit, not in your mind, but in science. So when we say the universe, we usually mean what we can see. What about the real world? It's a puzzle box. One we're stuck inside and can only see out of a tiny window that keeps getting smaller. The black hole firewall paradox, a burn line at the edge of knowledge. Black holes are already very strange because they bend space-time, eat matter, and hide data behind boundaries. But in the last few decades, theoretical physics has found something even stranger at their borders. A possible firewall. A quantum wall of fire that destroys anything that tries to cross the event horizon. And if it's true, it could be the most shocking limit of the universe there is. To understand the paradox, we need to revisit a foundational idea in black hole physics, the no-drama principle. This principle, rooted in general relativity, says that an infalling observer crossing a black hole's event horizon wouldn't notice anything unusual. The boundary is not a solid wall, but a smooth point of no return, dramatic in concept, but not in experience. You'd pass through without fanfare, until tidal forces tore you apart deeper in. But this serene image is challenged by a quantum dilemma known as the black hole information paradox. Quantum physics says that information can't be lost, which is the problem. But it looks like information about something that falls into a black hole is lost forever. That goes against the rules that control particles, chances, and the way reality is put together. So scientists started looking for a way out. The firewall theory, which was put forward by Almheri, Marolf, Polkinski and Sully in 2012, is a controversial approach. They said the event horizon of a black hole might not be smooth at all. It could instead be a wall of particles with a lot of energy, a barrier so strong that anything hitting it would turn to steam. No easy way through. There is no quiet bridge. It was just total destruction. There was a big disagreement in theoretical physics over this idea. Some people who believe in general relativity said that smooth boundaries are necessary for space-time to be continuous. Quantum scientists, on the other hand, said that unitarity, the idea that information must be kept, requires a compromise. There must be a catch. That something could be Einstein's no-drama line. But why would there be a firewall? It has to do with the entanglement between particles inside and outside the black hole. As a black hole emits Hawking radiation, quantum theory demands that the outgoing particles stay entangled with their partners inside. But this violates another quantum rule called the monogamy of entanglement. A particle can't be fully entangled with two different systems at once. So, to resolve this, the firewall hypothesis suggests that the entanglement is broken. And when that happens, energy explodes at the horizon. The event horizon turns into a death trap. This isn't just a hard math problem. It gets to the heart of things. We don't fully understand space, time, and gravity if fences are real. Even worse, there may be times in the world when reality not only doesn't allow us to observe it, but it actively pushes us away. If you're too curious, a black hole might not even be a hole at all. It might be a limit with teeth that makes you feel bad. It's not just the science behind the firewall dilemma that scares people, it's the not knowing. We still don't know if fences exist 10 years after the idea was first put forward. There is no clear proof from observations, no agreement, and no trial that can settle the question. We only have thought tests and the scary thought that we might be getting close to the event horizon of being able to know anything. The shrinking horizon. Why we'll see less each year. Most of the time, we mean growth when we say expanding horizons. More information, more discoveries, and a clearer view of the universe. However, in a terrible cosmic twist, the reverse is taking place. Our view of the world is getting smaller, and it will get even smaller as time goes on. Let's back up. We know that the world is getting bigger. When Edwin Hubble made his finding in the 1920s, it showed that galaxies are moving faster the farther away they are. Not because we are in the middle of the universe, but because space is getting longer. Not only is the growth still going on, it's speeding up. This is caused by an unknown force called dark energy that is built into space-time itself. A scary fact is that light from faraway galaxies can no longer reach us because space is expanding so quickly. At this very moment, the galaxies that are very far away have been giving off light for billions of years, and those photons are just now reaching our telescopes. But a lot of those galaxies are already moving away from us faster than light. It's not because they're moving quickly through space, but because the space between us and them is getting bigger. This doesn't go against the rules of relativity either. In space, things are not going faster than light. Space is growing, which is possible because of general relativity. So what happens to those galaxies? They fade. They redshift into invisibility. Their light gets stretched to longer and longer wavelengths until it moves past the range of our detectors. And eventually, they're gone. Not because they cease to exist, but because their signals can no longer reach us. We are not gaining access to more of the universe over time. We're losing it. In the distant future, billions of years from now, our observable universe will be much smaller than it is today. Distant galaxies will have disappeared from view. The cosmic microwave background will stretch into undetectability. The universe will look increasingly empty. Not because it is empty, but because the evidence of its vastness will have slipped beyond our horizon. This shrinking horizon has deep implications. It means that now is the best time in cosmic history to study the universe. We're living in a brief window when the most evidence is available, when ancient light is still arriving, and the distant galaxies haven't yet vanished behind the cosmic curtain. Pretend that people in the future live in a galaxy cluster that is completely cut off from everything else. They can only see a few nearby galaxies. There is no radiation from space. Hubble did not expand. It's possible for them to think that their world is fixed, small, and eternal, just like people used to think before modern astronomy. And that's the scary truth. Our job as cosmic explorers is to find records that are quickly being erased. We'll know less and less as time goes on. The book is being closed not because our tools are weak, but because the world itself is. The dark flow, a possible signal from beyond the observable universe. We think that what we can see is the whole universe, and there's a good reason for this. That's how long it takes for science to get to us since the Big Bang. It's the limit of both light and time. But what if there is something beyond that limit that is pulling on the universe in ways we can see, even though we can't see where it comes from? That's the puzzle at the heart of what scientists call the dark flow, the strange movement of galaxy clusters that can't be explained. Discovered through data from the Wilkinson Microwave Anisotropy Probe, WMAP, and later refined with other cosmic microwave background, CMB, observations. The dark flow refers to a peculiar, coherent movement of galaxy clusters across the sky. These clusters appear to be drifting at high velocities. Some estimates suggest up to 1,000 kilometers per second toward a particular region of space. This wouldn't be so odd, except that the region they're heading toward lies beyond the observable universe. Cosmologists have tried to explain this using known physics. Some speculate that local gravitational anomalies or massive structures, like great attractors or supervoids, might be behind the motion. But no explanation inside the observable cosmos fully accounts for the behavior. What's even stranger is the uniform direction of the movement, like a tide moving galaxies, as though a distant current were pulling the universe towards some cosmic drain. What if the dark flow is caused by the pull of a huge structure beyond the edge of the universe? There is something we can't see that still has an effect on us. That would mean the world we can see isn't a separate bubble of space-time. This thing is part of a bigger structure, like a multiverse, or a mix of cosmic regions that affect each other in very small, almost imperceptible ways. This changes the way we think about the limits of the universe in big ways. It means that gravity might not be limited by the same things that we can see that limit light. Even though we can't see what's pulling those worlds together, we might be able to feel its pull. And if that's true, it calls into question the idea that the cosmic horizon is a clear line between what we know and what we don't know. Skeptics warn that the data could be taken in the wrong way. Some say that the CMB's dipole anisotropy, changes in temperature and intensity, could be making it hard to understand. Others say that the dark flow hasn't been shown to be real with newer, more accurate tools like the Planck satellite, and that some studies have found very little to no proof of it. But there's a problem with just ignoring it. The signal is still there. Yes, it's weak, without a doubt, vague. It is regular enough, though, to be worth looking into. And if more tools prove it, if the flow keeps going, then we might be on the edge of something huge and secret, like the moon pulling on the tides, but it never shows its face. Picture yourself in the dark at the edge of the Grand Canyon. There is a breeze coming from the other side, but you can't see it. It's soft and steady. The air is moving, but you don't know what it is. That's the dark flow, a breath from beyond what we can see that tells us that what we see isn't all there is. The cosmic information limit, when reality itself stops transmitting. People often think that we could find out a lot more if we had better cameras, bigger monitors, or faster computers. But the world itself has a design flaw that can't be fixed by technology, society, or any amount of creativity. This is known as the cosmic information limit, and it tells us not only what we can see, but also what information can exist. This limit is based on entropy, which is the slow loss of order and gain of disorder. Entropy keeps going up as the universe ages and grows bigger. There is more energy all around. Strongholds fall apart. And most importantly, particles, light, and even gravity waves lose their power to carry useful information. There's more to it than just the fact that galaxies in the far distance are out of sight. The amount of knowledge that can be recovered and made sense of in the universe itself decreases over time. The loss of cosmic memory is a key part of this process. Things that happen leave marks, like ripples in gravity, bursts of light, and patterns of radiation. But these signs get stretched, redshifted, and lost in background noise as the universe ages. In the end, they blend together into nothingness. There would come a time when you could no longer figure out what happened, even if you collected every photon, neutrino, and gravity wave. This is predicted by the Bekenstein bound, a principle from black hole thermodynamics that says there is a maximum amount of information that can be stored within a given region of space. Beyond that, no matter how you configure matter or energy, you cannot encode more knowledge. Space itself has a memory limit, like a cosmic hard drive that can only hold so many bits before it starts overwriting or losing data. It's getting closer and closer to a state called heat death, which means that everything has broken down into a state of greatest chaos. Not a single star, structure, or change. There won't be any more energy differences in that far-off future, so no new information will be being made. There won't be any purpose in the world. It will just be quiet. There will be noise everywhere. We feel like we're travelers who are learning more about the world as we go. From a cosmic point of view, though, we're in a race against a timer that will finally erase our tracks. It is a loss of history for all time that every star disappears beyond the cosmic limit and every signal goes silent. This includes history that can no longer be seen or heard. The Heisenberg Barrier, when quantum uncertainty blocks the view. You'll hit a wall if you zoom in too far, past molecules, atoms, and even protons and neutrons, not one in the real world but one in math, a line that is woven into the fabric of reality. It is called the Heisenberg uncertainty principle, and it's not just a bothersome thing to deal with when measuring. We can only know so much about the world because of this. In 1927, German physicist Werner Heisenberg revealed a truth that would shake classical physics to its core. The more precisely you try to measure a particle's position, the less precisely you can know its momentum, and vice versa. You can't know where something is and how fast it's going at the same time with perfect precision. There was nothing wrong with our tools. The way the lab was set up wasn't bad. It was just the way things are in the real world. This seems like a problem for experts who like things neat at first glance, but the effects are much bigger than that. There is always the Heisenberg barrier in the way when we try to see into the most basic parts of the universe, when we try to see the framework that holds everything together. Try to look at a particle more closely. It's affected by you. Try to find its energy with the utmost accuracy. Its location stops being known. Observation isn't passive at the quantum level, it's taking part. The thing you're trying to observe changes because of the measurement you use. Fundamental physics is going to have a very hard time with this. Imagine trying to make a full map of the world, but every time you look, the map gets shuffled. There is a world called quantum that does that. We will never get rid of this uncertainty, no matter how great our technology gets, because it's not a technical problem, it's a moral one. The uncertainty principle sets a hard floor on precision, not just in labs, but in the structure of space-time itself. To fully understand how particles behave, how they interact, and how quantum fields operate beneath the surface of existence, we would need access to an impossible level of detail, a level forever shrouded by quantum fog. It gets worse. This limit isn't just for little things. Different tests have shown that doubt grows. Quantum behavior can change whole molecules in certain situations. Quantum impacts could, in theory, reach cellular or even macroscopic levels if you could separate them well enough. We like to think that we can know the truth in the end, that we can get to the bottom of every puzzle if we take the time, be patient, and be very careful. The Heisenberg barrier, on the other hand, is always the same. A warning that what appears and what can be known are not the same thing. Some physicists have even speculated that uncertainty is not a bug in the system. It's a feature that keeps the universe stable. Without it, atoms would collapse, matter would behave wildly, and reality as we know it would unravel. The neutron star equation of state. Why matter's limit may be immeasurable. Neutron stars are the densest things that we can see in nature. After a supernova, these dead stars leave behind a cylinder that is bigger than a city and holds more mass than the Sun. Their gravity pull is so strong that atoms fall apart, and protons and electrons join together to form a sea of neutrons that is very flexible. But no matter how much we know about these very far-away stars, one important question remains. How dense can they get? That mystery revolves around what physicists call the equation of state for neutron star matter. It's a relationship that connects pressure, density, and temperature. Essentially, the rules that describe how matter behaves when squeezed into unimaginable tightness. For ordinary matter, we have equations of state for water, air, and iron. But for neutron star matter, we're mostly in the dark. The issue isn't a lack of theories. On the contrary, there are many competing models, from simple nuclear physics to exotic proposals involving hyperons, quark matter, or even Bose-Einstein condensates. But each of these models predicts a slightly different maximum mass and radius for a neutron star. And that matters, because beyond a certain threshold, the star collapses into a black hole. We might be able to figure out the real equation of state if we could very accurately measure the mass and radius of enough neutron stars. The catch is that we can't see what's inside them. Surface activity tells us everything we know. This includes X-ray data from space telescopes like NICA, gravitational wave signals from neutron stars crashing into each other, and pulses from black holes. These are just hints, not answers. Take GW 170817, for instance, the first neutron star merger observed via gravitational waves in 2017. It offered valuable clues about neutron star structure, especially during the milliseconds before and after impact. But even that data couldn't definitively reveal the true internal composition. The equation of state remains elusive. Like PSR J0740 plus 6620, which has a mass close to 2.1 solar masses, some neutron stars push the limits of what is known about mass. Softer models of state are put under a lot of stress, which rules out some of them. Others, like ultra-compact X-ray pairs, point to sizes that are very, very small. But once more, each discovery makes more models, not less. It's like trying to put together a puzzle where each new piece fits in more than one spot, and the picture never gets clearer. It's not just a matter of interest. We need to figure out how matter behaves at supranuclear densities, if quark matter is stable in mass, and if strangelet-like states of matter exist. The neutron star equation of state could help us do that. If we find that neutron stars interact with strange particles in new ways, it could even help us figure out what dark matter is. Why? We might never know. Because neutron stars are too good at keeping their stuff secret. Their insides are hidden by crusts that make it impossible to see directly. Their crashes happen in galaxies far away, where gravitational lensing and cosmic expansion change the shape of the impacts. And even if we make devices that are more sensitive, we will still only see effects that aren't the core itself. The bigger irony, it's possible that the densest, most extreme matter in the universe will never be able to be seen. It's not because it's too far away or too small. It's because of a wall that nature made. A spot where equations become vague, our tools only pick up whispers, and information stops, not at the edge of space, but at the center of matter. There are no black holes in neutron stars, but deep down they may be holding a different kind of singularity, one that is data. It's not a silence of nothingness, it's a silence of such deep depth that it can't be put into words. The quantum foam, beneath space, only chaos. Space-time would start to boil if you could get smaller than a proton, which is smaller than a quark, all the way to the edge of what is called the Planck scale. Not because of heat, but because of doubt. This is the area of quantum foam, which is a sea of temporary particles and wavy geometry that swirls and shakes. The term quantum foam was coined by physicist John Wheeler, who envisioned that at incredibly tiny scales, around 10 circumflex 35 meters, space-time isn't smooth like a rubber sheet. It's wild, jagged, frothy. Here, virtual particles pop into and out of existence. Energy fluctuations twist the fabric of space itself. The geometry of the universe breaks down into something closer to chaos than order. In classical physics, we imagine space as a backdrop, something constant and unchanging. But quantum field theory tells us otherwise. Even in a so-called vacuum, fields are still there, buzzing with energy, and that means even empty space is not truly empty. Quantum foam is what happens when you try to apply quantum mechanics to gravity. General relativity treats space and time as smooth and continuous, but quantum theory introduces randomness and graininess. Try to fuse the two, and at extremely small scales, smoothness gives way to madness. Space-time becomes quantized, like pixels on a screen you didn't know had a resolution limit. The Planck length is that length. There's just one problem. We can't test this right now. We haven't been able to build an experiment that can go this deep. not even the biggest and best gravitational wave instruments. We're not even close. It would take a particle collider the size of the galaxy and energies a trillion times higher than what humans can currently achieve in order to see quantum foam. So why do physicists believe in something we can't see? Because the math demands it. Without quantum fluctuations, many of our best theories unravel. The vacuum energy of space, for example, is a prediction of quantum foam. Theories like loop quantum gravity and string theory also suggest that spacetime is not continuous, but stitched together from microscopic units, vibrating strings, spin networks, or topological nodes that fluctuate in and out of being. This brings up a very important question. How do you describe a place if space and time are made of foam, or a time frame? Those ideas fall apart in the quantum foam. You can't really say before or after. There are only possibilities of how events might be related. And this is where things get tricky. Quantum foam might be the edge of what we can know. On this size, we can't fix anything, and we might never be able to. Not only do we not have the tools, but nature may not even let those tools exist. The Neutrino Wall. When even ghost particles go dark. There's a reason why we call them ghost particles. Neutrinos are some of the most difficult to find in the world. They go through regular things like light goes through glass. Right now, trillions of them are going through your body, and you won't even know. For many years, people thought they were light, flavorless wisps of life. However, they are very important to how stars burn, how supernovae explode, and maybe even how the universe formed in the beginning. But even ghost particles can only do so much. First, let us talk about what neutrinos are. Neutrinos are made in nuclear processes, both inside and outside of stars. They come in three flavors: electron, muon, and tau. They are very small particles with almost no mass that only interact with matter through gravity and the weak nuclear force. This makes it almost hard to find them. We only know they exist because of the effects they have on things that are far away, like huge deep tanks full of water, ice, or other strange materials used for detection. And yet, despite their ghostly nature, neutrinos are powerful messengers. We've used them to peek inside supernovae, to study solar fusion, and to test the fundamental symmetry of the universe. Their ability to travel vast distances without scattering makes them time capsules, cosmic postcards from distant cataclysms. Neutrinos lose their power, though. There are various methods by which neutrinos can go dark. First, the loss of energy. Neutrinos lose energy over cosmic timescales in the same way that photons do. This is because space expands and stretches the energy of both. It gets harder to find them as their energy drops. Today, a high-energy neutrino from a close supernova could set off monitors. But a neutrino with low energy from the beginning of the universe. It was so quiet that no microphone could pick it up, so it could drift through Earth without being seen. Second, background noise. Even in our best detectors, neutrino signals must be separated from natural background radiation, cosmic rays, and other rare particles. As the neutrino's energy decreases, its signal blends with noise. The difference between detection and silence becomes statistical, less a matter of data and more a matter of probability. There is a threshold below which we simply can't tell the difference between a passing neutrino and random static. Third, and perhaps most hauntingly, cosmic aging. Just like the cosmic microwave background, there exists a theorized cosmic neutrino background, CNB, a sea of ancient neutrinos left over from just 1 second after the Big Bang. These are the oldest relics in the universe. But we've never directly detected them. Why? Because their energy is so low, mere microelectron volts, that no current technology can capture them. They're everywhere, and forever hidden. That's the wall. The Neutrino Wall is more than just a ceiling on what can be found. It's a landscape of very quiet space. Even if we make devices the size of Earth and cool them down almost to absolute zero, neutrinos will still behave in a way that isn't being seen. This ceiling isn't set by engineers. It's set by the way reality is structured. In a universe slowly fading into thermodynamic quiet, neutrinos are among the last particles still whispering the story of cosmic birth and transformation. But even they fall victim to time. As the universe expands and ages, neutrinos redshift, decay, or become so dispersed that no detector, no matter how powerful, can distinguish them from the void. Particle colliders, smashing our way into the unknown. You smash something really small to understand it better. That's how particle physics has worked for almost 100 years. Scientists thought that atoms couldn't be split up until they made tools that could throw them at each other at higher and higher speeds. With each hit, smaller pieces like electrons, protons, and neutrons were exposed. Then quarks, gluons, and bosons, which are even smaller. Now, though, this method may have reached its limit. Our most powerful tool in this hunt is the particle collider, a circular racetrack where particles are accelerated to near light speed and forced to collide. The resulting energy and debris allow scientists to glimpse new particles, detect unknown forces, and confirm or reject the very theories that define modern physics. The Large Hadron Collider, LHC, at CERN is the reigning champion. With a 27-kilometer underground ring and energies reaching 13.6 trillion electron volts, it was powerful enough to confirm the existence of the Higgs boson in 2012. A particle once thought to be the final missing piece in the standard model of particle physics. The deeper we dig, the harder it becomes to keep going. To probe shorter distances, we need more energy, and the curve is brutal. To go from observing an atom to a nucleus, we needed electron volts. To see quarks, we needed giga-electron volts. To probe the Planck scale, where quantum gravity lives, we'd need 10 circumflex 19 GeV. That's 100 billion times what the LHC can do. To put that in perspective, we'd need a ring the size of our solar system to build a collider that could hit those levels of power. And even if we could find the ingredients and energy to make such a machine, there's still a problem. The benefits are decreasing over time. Every particle we find is like a small piece added to a very big puzzle. But the pieces that are still missing are in the hardest to reach places, like dark matter, quantum gravity, and the very beginning of space and mass. It's no surprise that some physicists are starting to ask the unthinkable. What if colliders can't take us any further? What if smashing particles is like smashing clocks to understand time, useful for a while, but inherently limited? Designs are being drafted for the future circular collider, a proposed 100-kilometer ring that could reach 100 TeV, 7 times the power of the LHC. Others dream of linear colliders, plasma Wakefield accelerators, or tabletop colliders that use lasers instead of magnets. Each of these could extend our reach, but only slightly. Not enough to crack open the mysteries of dark energy or peek behind the curtain of quantum foam. So, let's face a harsh truth. Ion colliders and atom smashers, which are some of the most powerful tools we have, may have a limit. There comes a time when adding more energy doesn't get us any closer to the truth. Instead, it just makes more noise, heat, and questions. There may be parts of the world that are so small, weird, and truly chaotic that this way of looking into them can't reach them. Gravitational wave limits, the vanishing ripples of cosmic catastrophes. In 2015, we heard something we had never heard before, not with our ears, but with detectors the size of buildings, a ripple in space-time, a chirp from 2 black holes colliding over 1 billion light-years away. That moment marked the birth of gravitational wave astronomy, and with it, a brand new sense, the ability to listen to the universe. It does have bounds, though, just like every other sense. Gravitational waves are ripples in space-time that are caused by very large cosmic events, like black holes hitting or neutron stars merging, or maybe even changes that happened when the universe was first created. Einstein's general theory of relativity tells us exactly how they act. They stretch and squeeze space as they go by. Our current detectors, LIGO in the US, Virgo in Italy, CAGRA in Japan, are exquisitely sensitive. They can detect changes in distance smaller than a proton, but even with that precision, we're only catching the loudest, most violent collisions, and only those within a few billion light-years. It's like hearing only the drumbeats of nearby thunderstorms, while missing the rain of distant worlds. And the signal is weaker the farther away the event is. It is the inverse square rule that says when you double the distance, the signal strength drops by a factor of 4. This is also true for gravitational waves. When we add in the expansion of the universe, which makes these waves longer and weaker, we quickly get close to a gravity wave barrier. This is the point beyond which ripples become so weak that they can't be seen. The issue compounds with redshift. As space expands, it stretches the wavelengths of gravitational waves, lowering their frequency. Many ancient signals, especially those from the early universe, are now so long wavelength that they fall outside the sensitivity range of our detectors. They're like bass notes below the range of human hearing, real but forever inaudible. Future observatories like LISA, the Laser Interferometer Space Antenna, aim to broaden that spectrum. Orbiting in space with arms millions of kilometers long, LISA will tune in to lower frequency waves from supermassive black hole mergers and galactic binaries. But even LISA has a flaw, and there are signals that no conceivable technology could ever catch. Theoretical sources like primordial gravitational waves, ripples from the inflationary burst that happened fractions of a second after the Big Bang, remain undetected. We might infer their presence through indirect signs, like polarization in the cosmic microwave background, but direct detection. That may never happen. Their wavelengths are too vast, their amplitudes too slight, their existence buried beneath cosmic noise and quantum uncertainty. What's more, gravitational waves suffer from a problem of cosmic entropy. Like all forms of radiation, they carry energy. As the universe ages and cools, that energy disperses. Eventually, even the most violent cosmic collisions will fade into silence, not because they didn't happen, but because the universe will no longer support a medium clear enough to let their whispers reach us. This makes me think of something unsettling. What have we missed already? A huge number of mergers and disasters happen every year in the deep sky. But only a very small number make it through the gravitational wave barrier and into our awareness. The rest are not heard. The quiet gets louder as the universe grows. We thought that gravitational waves would be our big break, our last sense key to the universe. But even they fade away into space, time, and distance. In the same way that light and neutrinos do, they hit a wall. The photonic dissolution when starlight becomes irretrievable. Photons are the messengers of the world. Photons are the building blocks of everything we see, including stars, nebulae, and galaxies. They are created in nuclear explosions or crashes between galaxies and travel through space for eons before they reach our eyes or instruments. Astronomy's history is a lot like the past of how to catch light. But what if the light itself is doomed to fade? As the universe expands, photons, massless packets of energy, suffer a silent degradation. Their wavelengths stretch, their energies drain. Over billions of years, the visible transforms into the infrared into the microwave into radio. Eventually, that signal dissolves into background noise. This process isn't hypothetical, it's observable and inevitable. It's called cosmic redshift, and it's already happening to nearly every photon we catch from the deep sky. This is photonic dissolution, the irreversible process by which even the most brilliant cosmic light is destined to vanish from detection. Imagine a photon emitted by a distant galaxy 10 billion years ago. When it began its journey, it may have been ultraviolet or visible light, but as the universe stretched, so did the photon's wavelength. By the time it reaches Earth, it may be microwaves or even radio waves, still technically carrying information, but now spread so thin and low energy that only our most sensitive instruments can detect it. And that discovery can only go so far. When photons redshift, they lose power. It's easy to see the connection. Energy is inversely proportional to wavelength. Light waves have less energy when their frequency is longer. Eventually, that energy drops so low that it can't be told apart from thermal noise, which includes random background signals from the Earth, our sensors, and even quantum fluctuations in space-time itself. This is not a technological limit. It's a physical one. At some point, the signal-to-noise ratio becomes so poor that the photon effectively ceases to exist from an observational standpoint. It's still out there, technically, but it may as well be gone. And since dark energy is still speeding up the universe, this process speeds up too. More and more photons from galaxies far away are being stretched past the point where they can be detected. Light from brand new stars far away in the sky is being redshifted out of range before it even gets there. Parts of the universe are becoming inaccessible, not physically dark. There are two tragedies here. We're not only losing info, but we can't get it back. There is no record of the cosmos. A photon can't be recovered after it goes past that observing limit. There is no saved file, second wave, or cosmic hard drive that can hold what was lost. There is no reason for the world to repeat itself for our own benefit. This leads to a kind of existential expiration date for astronomical knowledge. In the far future, even light from our own past, now stored in the intergalactic medium, will fade into undetectability. Scientists of the far future, perhaps even evolved humans or alien civilizations, will look up and see nothing, a static, empty sky. The cosmic narrative will have gone dark. How much of the light from long-ago stars has already faded away? What secrets about how galaxies form, how the universe is structured, or even how things were before the Big Bang can't be found? Not because they're hidden, but because they've just disappeared. People often say that rays are like ghosts from the past. The carriers do die, though. Light can be turned off, but not by distance or barrier. It can be turned off by the slow breakdown of space-time itself. Why we can't probe beyond the Planck length? At the tiniest size possible, the idea of space starts to fall apart. The Planck length is that size, which is about 1.616 x 10^3 meters. It's not just small. The size is so small that it's almost offensive. Just to give you an idea, a proton is about 100 million trillion times bigger. It's like trying to read the small print on an atom from the other side of the universe if you try to zoom in any further. Why is this particular length so important? Because it's the scale at which gravity and quantum mechanics, two of the most successful theories in physics, collide, literally. At lengths larger than the Planck scale, we can describe gravity using Einstein's general relativity, and we can use quantum field theory to describe the particles and forces of the subatomic world. But below this line, these two frameworks fall apart. Space and time themselves are no longer smooth but jittery, chaotic, dominated by what physicists call quantum foam. Now, you might ask, well, why not just build a microscope powerful enough to see it? Here's the catch: physics forbids it. To observe anything, we must use energy. But the smaller the object, the more energy we need. At the Planck length, the amount of energy required to probe that space would be so great that it would collapse into a black hole. You'd be trying to observe something so tiny and packed with energy that your very observation would destroy the thing you were trying to see. This isn't just a problem with technology. This is an important limit. You shall not pass, says nature herself. There are now a lot of scientists who think that the Planck length is the smallest unit of space, or pixel of the world. Below that, the word smaller might not even make sense. It's possible that there is no bigger. Like a computer picture, space can be quantized, and the Planck length is the smallest size that can be used. There are theories, like loop quantum gravity and certain interpretations of string theory, that try to describe what happens at or below this length. Loop quantum gravity, for instance, treats space itself as a woven network of finite loops, while string theory suggests particles are one-dimensional strings vibrating at different frequencies. But even these cutting-edge theories are speculative and untested at the Planck scale. We have no empirical data, no observations, and no way, at least for now, to get them. What this means is frightening. The rules of nature make it impossible for us to know what lies below the Planck length. It's not that we aren't smart enough, wealthy enough, or patient enough. They are just that. Like an old picture, our world may have a resolution limit that is built in. You can only zoom in so far before the picture blurs, then turns into dots, and finally into noise. And so we find ourselves staring at a cosmic boundary, not one of distance or time, but of understanding. A wall not made of stone or steel, but of epistemology. We're not just limited in what we can see. We may be limited in what we can even conceive. Information hiding in quantum fields. At first glance, the world looks like it is made up of things like planets, stars, atoms, and particles. But if you look more closely, you might find that everything we see isn't really made of stuff in the usual sense, but from fields that we can't see but are everywhere. Particles are not basic in modern physics, especially when it comes to quantum field theory, QFT. Instead, they are short-lived waves, or quantum excitations, in a field below. Each type of particle, from electrons to quarks to photons, corresponds to a different quantum field spread out through space. These fields are everywhere, even in the darkest, emptiest voids of space. When undisturbed, they are calm, quiet, but agitate them, and they produce what we call a particle. In essence, reality is a field, and everything we think of as matter or energy is just a wrinkle in it. These fields can store information, not like a USB stick or a hard drive, but in much subtler, almost spectral ways. According to the holographic principle, information about a volume of space could actually be encoded not within that space, but on its boundary. This stems from studies in black hole thermodynamics, where the entropy, a measure of information of a black hole, is found to scale with its surface area, not its volume. If this principle applies more broadly, then all the information inside a region of the universe could be projected or preserved on its outer shell, its cosmic skin. And that means we may never truly gain direct access to what's inside the universe's deepest layers. We may be like shadows on a wall, studying our silhouettes and mistaking them for the source. On top of that, quantum fields are never really still. Even in a perfect vacuum, there is a jitter or a baseline energy called vacuum energy. This energy is what makes things happen, like the Casimir effect, where two metal plates in a vacuum are drawn together by changes in the quantum field. This rumbling, unseen background hum has a lot of energy and, more importantly, important knowledge about how the world works at its core. But again, we hit a limit. We can't directly see these fields. We infer their presence through indirect effects, interactions, decays, noise in our detectors. But just like we can't see wind, only the leaves it stirs, we can't directly observe the quantum fields themselves. The information they carry is encoded in a language we can barely interpret and may never fully translate. Quantum decoherence is another scary idea. This is when information in a quantum system is lost to the world and can't be recovered. Not lost, but mixed up with everything else so much that it might as well be. One reason quantum computing is so hard is that data is easily lost and is always spreading out into the universe. Do we live inside a probability wave? The further we go into the quantum world, the less solid reality seems to be. The clear rules start to get fuzzy, certainty goes away. We can't help but wonder if the world isn't really a place we live in, but rather a wave of possibilities that we're riding. There is a strange truth at the heart of quantum mechanics. Until it is noticed, nothing has a clear position, speed, or even presence. Before anything is measured, it is defined by a wave function, which is a mathematical object that stores all the possible results of a system. Where an item could be. It's possible to do. It doesn't even matter if it exists at that time. This wave function doesn't collapse until an observation is made. Until then, the particle exists in a superposition of states, a fuzz of all possible realities. And this isn't just some artifact of flawed measurement. This is what experiments consistently show us. Reality at the most fundamental level is statistical. Take the famous double-slit experiment. Fire a single photon toward a barrier with two slits, and if you don't measure which slit it went through, it behaves like it went through both. Over time, a pattern emerges, an interference pattern that reveals the photon's wave-like nature. But measure which slit it goes through. The pattern collapses. The wave disappears. The particle chooses a path. The catch is that we're a part of that system. We are made up of tiny pieces. Wave functions tell those particles what to do, your atoms, your ideas, what you did. It's possible that everything you are comes from clouds of chance. This isn't a figure of speech. It's not about philosophy. It's just math. It's getting weird. The many worlds view of quantum physics says that whenever a quantum event could have more than one result, they all happen, but in different parts of reality. In this view, the world is always splitting into an infinite number of possible outcomes, each with its own form of me, you, and everything else. Reality stops being a straight line and starts looking like a tree with many branches. Now, what does that mean for limits? It means what we perceive as one universe may only be a single thread in a much larger quantum tapestry. We might not be seeing the whole picture, not because it's far away or too small, but because we are embedded in one slice of something fundamentally probabilistic. And this means something very important. What we think we know may always be smeared. There is no way to know for sure what the universe is made of, not even with the most advanced tools and measures. There will always be doubt, not because our tools are broken, but because that's how things are in the real world. If this is true, then the limits of what we know might not be walls at the edge of space or energy, but the very edges of reality. That is, we might live in a universe ruled by chance instead of just living in one. One more thing in a field of possibilities that keeps growing. Schrödinger's limits. What can never be known? In 1935, physicist Erwin Schrödinger posed a bizarre thought experiment. A cat, locked inside a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decayed, the poison would be released, and the cat would die. If it didn't, the cat would live. But quantum mechanics said the atom was both decayed and undecayed, until observed, which meant, in theory, the cat was both dead and alive, until someone opened the box. What Schrödinger meant as a critique of quantum absurdity has since become a defining symbol of its strangeness. But this cat-in-a-box scenario isn't just weird. It points to one of the most sobering truths about our universe. There are things we may never be able to know. It's not because we're too simple, not because we don't have any ideas. Real life won't give up its secrets without killing them first, though. Indeterminacy at the quantum level is based on this. Observation doesn't just show a fact in quantum physics, it makes the fact. Particles are probability waves before they are measured. But the wave breaks apart as soon as we try to get information from it. What we wanted to know changes when we know it. And this isn't just about particles. This limit to knowledge exists at every scale where quantum mechanics operates. Try to pinpoint the position and momentum of a single electron, and Heisenberg's uncertainty principle jumps in to stop you. You can know one, but not both. The universe won't allow it. Quantum coupling, on the other hand, is where two particles are so closely connected that measuring one immediately changes the other, even if they are very far apart. It's like data is flying between them faster than light. But there's a catch. The outcome is chance. It's not possible to send a message. It can't be used to guess what will happen. You can only look at what is already mixed up and wonder what it all means. Some physicists argue that quantum randomness isn't real, that there must be hidden variables, things we just haven't uncovered yet. But the most powerful experiments to date, including Bell test experiments, consistently support the view that randomness is fundamental, not ignorance, not lack of data, but a ceiling, a hard-coded limit. So, Schrödinger's cat isn't just a riddle. We should be careful not to cross certain lines because they could damage what we're trying to keep. We can't get some answers back without deleting the question first. While we make devices that are smarter and smarter, smash particles together at impossible speeds, and look into the dark space between stars, we have to face the blind spots we'll never be able to light up. The brain bottleneck. How much can a mind really hold? As people work to make bigger antennas and figure out how to code ever tinier particles, a quiet, unsettling truth starts to come out. There may be limits not just out there, but also here, inside our own heads. Everyone agrees that the human brain is amazing. It's the most complicated thing we've ever found in the world. It has about 86 billion neurons and more than 100 trillion synaptic links. We've been able to write symphonies, send satellites into space, and guess what will happen to time itself. But for all its brilliance, the brain is not infinite. It is biological hardware, evolved to ensure survival, not cosmic comprehension. It's time to start with memory. Brains are thought to be able to store around 2.5 petabytes of information, which is about 3 million hours of TV shows. Pretty cool, yes, but it still has a limit. It's even worse that we can't control how it's used. We forget things. We delete memories. What we remember is skewed. That 2.5 petabytes isn't a perfect hard drive. It's a sieve that's always moving and letting data through. We can only process a few dozen bits of information per second. That's a trickle, not a torrent. In a world where data floods in at gigabytes per moment from sight, sound, touch, thought, and language, we're bottlenecked at the very moment we try to think clearly. This bottleneck is why we lose track of conversations, forget why we walked into a room, or struggle to juggle even 4 or 5 variables in our heads at once. Our brains evolved to think in linear cause and effect, to reason in simple chains, if X, then Y. But the universe doesn't play by those rules. Quantum mechanics, chaos theory, emergent systems, they all operate on non-linear, often counterintuitive levels. You need powerful mathematics, computer simulations, and abstract models just to keep up. As a result, we use more and more tools that our brains weren't made to use as we learn more about physics, astronomy, and information theory. When we need to, we turn to metaphors and comparisons. But those break down eventually. This is where our imaginations start to run out. Could a mind really understand string theory in 11 dimensions? Or fully picture a closed circle that looks like time? Or really understand what it means for a particle to be in more than one place at the same time? Perhaps not. Maybe no living mind can. Even if we develop artificial intelligence that can, that doesn't guarantee we'll be able to interpret what it discovers. If a superintelligence cracked the true nature of quantum gravity, could it explain it to us in words? Or would the knowledge remain locked behind a wall of incomprehensibility, true but unreachable? Memory and mortality. The fragile bridge to cosmic truth. Each new group of scientists builds on what the previous group found. The way we understand physics, chemistry, biology, and cosmology is like a shuttle run of ideas that has been going on for thousands of years. Still, each person in this race is only there for a short time. Everyone only has a few decades to live, and their brains forget as much as they remember. Not only do time and chaos make us lose information, but also our own short lives. Take a nap. It's not optional, it's mandatory. We spend nearly a third of our lives unconscious, our brains busily sorting through memories, consolidating some, discarding others. It's an elegant biological process, but one with a cruel twist. You don't get to choose what sticks. Memories fade, details blur. Ideas once vivid slip silently away. It gets worse as you age. As neurons die and synapses fire incorrectly, our ability to remember things gets worse. Alzheimer's disease, dementia, and other neurological diseases are very cruel. Many years of learning can turn the mind into a locked vault, with the keys being lost as the body slowly breaks down. That's not all that's sad about this. It's a space one, because the world doesn't send the same word over and over. One discovery, like a gravitational wave from a faraway crash, might not happen again in our lifetimes. It's gone if we forget about it or miss it. Even the most brilliant human minds, those who expand the boundaries of theoretical physics or decode the messages of ancient light, are eventually silenced by time. Their insights survive only if written, recorded, or passed on. But even then, context is often lost, nuance fades, and ideas can be misunderstood or forgotten altogether. When we look at more than one person, the problem gets worse. Of course, civilizations can forget too. Books are burned, an empire falls, wars wipe out information. Years of knowledge can be lost in just one generation during a dark age. There is no promise of progress. The spark is weak and flickers in the wind of events. So, we make tools to fight back. We make books, computers, records, and storage in the cloud. We make AI to help us think and remember things better than we can. We send information to digital clouds and keep genes on silica. And yes, even computer memory can go bad after a while. Hard drives break down, formats become old. Even the best preserved information will eventually be lost because of quantum-level breakdown and cosmic radiation. And while we've invented tools to stretch memory beyond the brain, we haven't yet solved the ultimate constraint. We die. And when we do, the sum of what we've known, the connections, the instincts, the leaps of logic that defined our experience, dies with us. Can we simulate the universe? The boundaries of digital reality. If the world is too big to measure and too complicated to fully understand at once, then maybe simulating it is another way to find out what it's all about. Make a copy in digital form, add up the numbers, change the factors, check out what breaks and what shows up. But this answer, which seems to have no bounds, has hard limits on both its power and its usefulness. First, let's define what we mean by a simulation. In this context, it's not just a game or a model. It's an attempt to digitally reconstruct all relevant laws and initial conditions of a physical system, so accurately that the behavior of that system within the simulation mirrors reality. The idea is seductive. If we can simulate a star, we can learn how stars live and die. If we can simulate an entire galaxy, we can study dark matter's role in shaping it. And if we could one day simulate the whole universe, then maybe we'd finally understand its structure, its fate, and perhaps even its origin. But the challenge is staggering. Even with modern supercomputers, simulating a single supernova explosion, one star's violent death, requires weeks of processing and trillions of calculations. Now imagine trying to simulate all stars, all galaxies, and every quantum interaction at every point in time. To simulate the whole world that can be seen down to the atomic level would take a lot more computing power than we have now. The amount of information in the visible world is thought to be around 10 circumflex 120 bits. That's such a huge number that it's much bigger than all the data storage on Earth right now. We would still need a computer the size of a galaxy to finish the job, even if we took shortcuts, like only looking at big structures or modeling average actions instead of individual particles. To the point, some scientists think that the only quantum computer that could accurately model the universe would be one the size of a black hole. Then there's the energy problem. Computers require power. Massive simulations require massive energy input, and eventually, even if we constructed Dyson spheres or captured the rotational energy of black holes, we'd be bound by the thermodynamic limits of computation. Each bit of processed information costs energy. That's not just engineering, it's physics. What if we made a machine that was strong enough to model the universe? Would we trust it? Every model is an approximation. Assumptions are used in all simulations. Bias, mistakes, and missed science can happen to even the best ones. We'll get bad results if we put in bad info. That's not a bug. It's the edge of what we know. And there's a final twist. What if we're already inside a simulation? The so-called simulation hypothesis, popularized by philosopher Nick Bostrom, proposes that if it's possible to simulate a universe, and if civilizations ever gain the power to do it, then simulated realities might vastly outnumber real ones. That would make it more likely that we ourselves are living in a simulation than in a base-level reality. It's a wild idea, but one with serious philosophical consequences. We still have the same limits, whether we are in a game or making our own. We can't simulate things we don't know how to do. And we can't do more math than physics lets us. It's possible that the world is analog, unstable, and run by things that can't be digitized at all. Yes, we can make copies of parts of the universe. We can make echoes of the Big Bang, models of star groups, and close approximations of quantum systems. But making a model of the whole universe? That might be out of our reach forever. The illusion of continuity. Why spacetime may not be smooth. Time and space seem to flow together for most of us. We don't jump from one atom to the next as we move through space. On a clock, seconds go by slowly. We think the world flows with no breaks or stops, like a movie that plays at an endless number of frames per second. But this could just be a trick. At the deepest level, scientists think that reality isn't smooth at all. Beyond what we can see, and even beyond the most advanced tools, there may be a quantized structure to reality itself. It could be a fractured universe where space-time itself, not matter or energy, makes up the smallest building blocks. Let's start with the idea of the Planck length, roughly 1. 6 × 10 to 351. 6 times 10 circumflex, minus 35 1. 6 1 10 to 35 meters. It's a number derived from fundamental constants, the speed of light, Planck's constant, and the gravitational constant. It represents the smallest meaningful unit of length. If space were a screen, this would be its resolution limit. Any attempt to probe below that length runs into a wall, not because we lack technology, but because physics itself breaks down. At the Planck scale, the very notion of position becomes meaningless. It's the same with time. The Planck time, about 5, 4 bar 10 to 445. 4 times 10 circumflex, minus 44.5, 4 or 10 44 seconds, is the shortest measurable duration. Any effort to observe changes on that scale becomes self-defeating. Your act of measurement injects so much energy that it distorts spacetime beyond recognition. Reality starts to foam, a chaotic soup of uncertainty, fluctuation, and curved geometry. This leads to the concept of quantum foam, proposed by physicist John Wheeler. At ultramicroscopic scales, the smooth fabric of spacetime is replaced by a bubbling, jittering chaos. Wormholes open and close, loops twist in and out of existence, and geometry becomes probabilistic. If our universe were a road, this would be the gravel beneath the asphalt, and it may be the true foundation of reality. Why does this matter? This is because it means we can only know so much. There is a point past which reality won't work with us, no matter how strong our tools or how fast or accurate our computers get. You can't split space and time forever. There isn't a button that adds more zoom. At some point, you'll hit static. This has serious consequences for everything from quantum gravity to black hole information loss. It suggests that our current theories, general relativity and quantum mechanics, are incomplete. They describe smooth fields and continuous variables, but the real universe may be running on something more like a cellular automaton or a cosmic grid. Some ideas go even further. Loop quantum gravity, for instance, says that space is made up of distinct loops, which are very small units of volume that are linked together. Causal set theory sees reality as a collection of separate events that are linked by causes and effects. Even though string theory is still based on smooth geometry, it points to unseen dimensions where all known particles, and maybe even space-time itself, are made of compacted, quivering strings. The quantum eraser, undoing reality itself. Imagine a world where cause and effect aren't just fuzzy, but can also go in the opposite direction. In this case, what you do now seems to change what happened before. It's not science fiction. It's the strange world of the quantum erasing experiment, which is one of the most unsettling and strange facts in all of physics. It starts innocently enough, with a double-slit experiment, a foundational test in quantum mechanics. Fire individual particles, like photons or electrons, at a screen with 2 slits. If you don't look at which slit the particle goes through, the result is an interference pattern, like ripples overlapping in a pond. But if you do observe which slit the particle travels through, the interference vanishes. It's as if the act of measurement collapses the wave of probabilities into a solid fact. You can now go into the quantum eraser. Some scientists have set up the experiment in a very strange way. The which path information, which tells us which slit the particle went through, is stored but then erased after the particle has hit the screen. However, the interference pattern comes back after the which path information is cleared, even though the particle has already gone down. How is it possible? How can a choice made after a particle has arrived seem to change how it behaved before? Do we break the rules of causality? Is history being changed by the universe? But quantum physics says that the answer is not in retroactive cause, but in entanglement and coherence. We can't explain one particle or system correctly if we erase information about it because it is related to another particle or system. The past didn't change, but what we know about it did. You can only know certain things in the quantum world, so you can only know certain things. This creates a limit that feels less like a wall and more like a mirage. It reveals that the boundary between what is and what was might not be as stable as we assume. That reality is not just affected by observation, but by the possibility of observation. The quantum eraser brings us to a scary edge. What if the universe isn't a list of events, but a mess of connections? What if the idea of causality is just a nice fantasy for humans, and the real world is more like a puzzle, where things only make sense when you put them in a certain context? Some theories say that this experiment proves that knowledge is the most important thing in the world. This means particles are not things, but rather solutions to the questions we ask. Some say it's just a smart way to use statistics. Reality doesn't set in until we look, and sometimes not even then. This is true no matter what point of view you take. It's not just that this project blurs the line between the past and the future. It makes you wonder if that line even exists. There are different kinds of truth, and knowing something can change what is true, even in different times. One of the strangest bounds is in that idea. It's not a barrier of space or energy, but a border built into the logic of knowledge itself. The edge of chaos, when predictability breaks down. In traditional physics, you can tell what will happen if you know where everything is and how fast it's moving. That is what Newtonian determinism promises to be true. The whole world works like a clock, ticking along perfectly. Nature, on the other hand, doesn't like being that dependable. Chaos theory is the study of systems that are so sensitive to their starting conditions that even the smallest change can cause results that are very different from what was expected. This isn't just chance. This is called predictable uncertainty, and it has huge effects on how much we can know. Look at the weather. We can draw it. We can find out how big it is. But long-term predictions fall apart when it comes to doubt. Today's gust of wind over the Sahara could make or break next month's rain in New York. This is the butterfly effect. And it's not just a figure of speech. It's a scientific fact. Chaos isn't just storms and road jams, though. It goes deep into biological processes, natural networks, and even how galaxies move. Anything with feedback loops, outputs that change what comes in next, can become chaotic. In general, these structures are not impossible to understand. It's that in real life, they become too sensitive to handle. It's pointless to try to measure them accurately enough to guess what will happen in the future. In a chaotic system, rounding a number by even a billionth can send your simulation spiraling off into a totally different trajectory. And quantum uncertainty compounds this problem. Even if you had perfect initial measurements, the fuzzy boundaries of quantum states bleed into classical chaos, creating systems that are both uncertain and hypersensitive. This is important because a lot of processes in the real world are not straight. In other words, their results don't follow a neat scale. If you double the input, the result could triple, flip, or fall apart completely. Because of this nonlinearity, even small mistakes can have huge effects. So what is the end of the universe? We don't lack facts. It's that the info might be too complicated to use without it breaking down. No matter how fast our computers are or how accurate our readings are, we will never be able to get to some systems. Some scientists propose that chaos creates an epistemological event horizon, a kind of boundary beyond which prediction is not only impractical, but impossible in principle. We can still describe the rules that govern chaotic systems, but we can't use those rules to know exactly what will happen. In a sense, the closer we look, the less we can tell. And if our world is truly unstable at all levels, microscopic, macroscopic, and cosmic, then we can't know what will happen, be in charge, or be sure of anything. Chaos theory makes us realize that the limit isn't always about size or speed. Structure, the inner logic of systems that dance just outside of what can be predicted, is sometimes what it comes down to. It's possible that the world doesn't hide everything, but just enough to keep us wondering. Entropy's empire, the cosmic march toward heat death. There's a silent conqueror at work in the universe, one that doesn't roar like black holes or burn like stars. It's entropy, the slow, inevitable slide of everything into disorder. And if we're looking for a true limit, an inescapable endgame, it might be this invisible tide. Stress and energy are at the heart of chaos, specifically about how energy stops being useful after a while. When a system is closed, the second rule of thermodynamics says that entropy always goes up. It goes from being organized to being a mess, from hot to cold, from alive to dead. In terms of space, the stars go out, things become thin, and in the end, everything ends. But this is where things really start to creep me out. The universe is a closed system. It doesn't have any outside to bring new energy into it. That means that over unbelievably long periods of time, all processes come to an end. All the flames go out. This is known as the heat death of the universe. It's a state where everything is equal and no work can be done. Not a star, no life, nothing in place, and it's not a big blast. It's so quiet that it hurts. This isn't just a guess. Observations show that the world is growing, and it is getting bigger faster. It's getting farther apart between galaxies than ever before. Over time, galaxies far away will become invisible, passing the cosmic event horizon. Even the nearest stars will be gone in a very long time, wiped out by chaos and lost in the cold of space. Black holes, those great monsters of gravity, won't escape either. They'll evaporate via Hawking radiation, losing mass until they wink out of existence. It's a slow death, but a death nonetheless. What's left? Sparse particles drifting in near absolute zero. And after quadrillions of years, not even that. The scary truth is that entropy doesn't just limit systems, it also limits what we know. When you measure, compute, or make a discovery, you use energy. And the energy that can be used for these things goes down as chaos rises. That means we can only process, store, or get back a certain amount of information at a time. Entropy isn't just when stars die, it's the end of memories, the end of being aware. Even the information we think we've preserved, data etched in stone, encoded in DNA, or buried in silicon, will eventually succumb. Cosmic rays, quantum fluctuations, and thermal degradation ensure that nothing stays legible forever. Over the longest timelines, everything decays. Some theorists even speculate that entropy is the ultimate boundary to consciousness. That thought itself, requiring structured patterns in matter and energy, may vanish as the universe dissolves into thermodynamic equilibrium. It's scary to think that the end of the universe won't be a big show, but a slow, endless fade into nothingness. The last truth we'll find isn't about what's out there, but about what will never be again. Entropy does more than just mess up things. There is less hope for change. In doing so, it sets one of the clearest limits on the world. The cosmic censorship conjecture, when the universe hides its secrets. Think of the universe as a stage, with galaxies, stars, and the story of the universe expanding and contracting. Now, picture a curtain. Something unbelievable is happening behind the curtain, but the script won't let you see it. That's what the cosmic censorship conjecture, a big idea in theoretical physics, is all about. Proposed in 1969 by physicist Roger Penrose, the conjecture suggests something extraordinary. The universe doesn't allow us to observe naked singularities, regions where gravity becomes infinite and the laws of physics break down, unless they're safely hidden behind an event horizon. In other words, nature censors its most chaotic secrets. To understand this, we need to revisit the singularity itself. According to general relativity, when a massive star collapses under its own gravity, it doesn't just form a dense object. It collapses to an infinitely small point, a singularity. But this creates a paradox. At a singularity, space, time, and physical law all cease to be meaningful. It's a place where physics loses its grip. If left exposed, naked, such a singularity would bring unpredictability into the observable universe. Penrose's conjecture is a kind of protective law, a cosmic firewall that ensures singularities remain tucked away inside black holes, guarded by their event horizons. It's like the universe saying, yes, there's madness here, but I won't let it infect everything else. The catch is that we don't know for sure if this theory is correct. Cosmic filtering has been studied for decades, but no one has been able to prove it. In fact, naked singularities do show up in some models and strange space-time shapes, at least on paper. In certain situations, like in space with more dimensions or around black holes that spin, some scientists say that singularities might be able to be seen. That means the world might not always hide when it breaks down, and the consequences are huge if the curtain is pulled back even once. Naked singularities would allow information to emerge from places where time and causality break down. They could expose new physics, unknown forces, or even loopholes in our understanding of determinism. Some theorists have speculated that a visible singularity could function as a natural time machine, looping causality into paradoxes. If singularities ever become visible, our current physics can't handle it. Predictions stop making sense. Outcomes become chaotic. Even quantum mechanics, our other great pillar of modern science, can't resolve the issue cleanly. It would mean that reality itself might be fundamentally unpredictable in a way we've never experienced. Many scientists hope that cosmic control is real, not because they want to hide the truth, but because if it's not real, reality might become impossible to figure out. What does this tell us about how far the world goes? It could be this: we don't have to find every secret. Some things, like singularities, might be locked behind an event horizon that isn't just made of space and time. That's not because we aren't smart enough, but because space-time was made to hide them. Quantum cosmic censorship. Does the universe erase its own errors? Quantum theory takes over when classical physics fails, like when space-time bends too tightly or gravity breaks down into chaos. That being said, there may be more going on in the world than just running equations at the deepest levels of quantum reality. It could be actively doing what's right for its own stability. To understand this, we need to look at an idea that came about when quantum information theory and gravity physics came together. Space-time may act like a quantum error-correcting code. In digital computers, error correction makes sure that if a piece of data gets mixed up, the system can figure out what went wrong and get back to the original data. This is very important when working with sources that are noisy or not full. Now assume that the universe was doing this not to fix your broken files but to protect the framework of reality. It sounds wild, but in the last decade, theoretical physicists have been exploring how space-time geometry could emerge from the structure of quantum entanglement. Specifically, in a framework known as ADES-CFT correspondence, a duality between gravity and curved bulk space, and a quantum field theory on the boundary, researchers discovered that entanglement might weave the fabric of space itself. Plus, the tangling patterns look a lot like codes that fix mistakes. What does this mean? If you try to change or remove information from a certain area of spacetime, like by breaking a black hole's structure, the other parts of the system might fill in the gaps. It's like the world doesn't want to be deleted. It fixes itself to keep things like logic, clarity, and causality. That being said, quantum cosmic control might be even tighter than Penrose's idea. Aside from not being able to see naked singularities, we can't even see mistakes in the quantum fabric. There are no open contradictions or pure chaos, fixed code over and over again. If this is true, it could mean that we will never be able to watch certain events or acquire certain information because the world won't let us read those details. They are stored twice, locked behind entanglement, and can't be accessed unless you look at the whole system without any changes. This is something that no single viewer could ever do. It could also explain why black holes don't destroy information, despite appearances. If the universe uses quantum error correction, then what falls into a black hole isn't lost. It's scrambled, but not deleted. And when the black hole evaporates, that information may be re-released in subtle coded forms, preserving unitarity, the core principle of quantum mechanics. We can't ever separate or directly view certain things in this model because doing so would cause the whole system to change or heal. Reading only a part of a projection will change the picture, and the same is true for the quantum fabric. You can't pull truth out of it without losing the context that gave it meaning. To put it another way, reality is safe. We learn more about how the world works, and it seems that it doesn't just follow rules, it actively applies them with quantum-level accuracy. And what looks like a dead end to us might actually be a clever code doing exactly what it was made to do: keep reality consistent, even from us. The Bekenstein bound, a ceiling on how much you can ever know. There may be limits on not only where you can look, but also how much you can know about what's right in front of you. The Bekenstein bound is one of the most important and disturbing limits that has ever been put forward in theoretical physics. First conceived by physicist Jacob Bekenstein in the 1970s, this bound tells us that there is a hard cap on the amount of information any region of space can contain. Not because of technological shortfalls or observational blind spots, but because of the laws of thermodynamics, quantum mechanics, and gravity working together. Let's look at that in a bigger picture. Let's say the box is 1 meter wide. You can put anything in it, like light, fields, atoms, or even hard drive data. It doesn't matter how advanced your technology is. You can only fit so much knowledge into a certain amount of room. It's possible to store only a certain number of bits, and that number doesn't change with volume, but with surface area. That's the catch. It doesn't matter how big the box is on the inside. The important thing is how much surface area surrounds it. In everyday life, this doesn't make sense. In the three-dimensional world we live in, we think that more room means more storage, but that's not how things work at the quantum gravitational edge of physics. Information, on the other hand, seems to be essentially two-dimensional. The idea behind black hole entropy is the same. This made Bekenstein think about black holes, and found that the area of their event horizon, not their volume, is related to their entropy, which is a measure of how much information is hidden inside them. Later, Stephen Hawking linked this entropy to the light that a black hole gives off, which suggests that black holes follow thermodynamic rules just like other systems. That made me realize something very important. Maybe the whole world works by the same rule. There may be a basic limit to how much information can fit in any given area. This means that there is a limit to what we can know, recognize, or compute. The holographic idea is another thing that it connects to. Suppose the Bekenstein bound is true. Then, information written on the surface that surrounds a region of space can describe everything inside it, not in a figurative way, to the point. All the physics inside an area, like stars, galaxies, and even brains, could be explained by quantum bits dancing on a border. It's the same as saying that your 3D world is just a simulation and that the real data lives on a 2D shell. This means that you can't go past the Bekenstein bound no matter how accurate your telescopes get or how strong your computers get. You can get close to it, maybe pack in info that's just a few bits shy of the maximum, but when you try to go over it, something breaks. Either your system breaks down into a black hole, or the things you think you know about physics are wrong. It's like the world is telling us, this much is enough. Even worse, you might not know how near the edge you are. The bound doesn't yell, it talks softly. You could be doing studies that are just on the edge of what you can know, and the only way you'll know is when your data starts to look strangely incomplete. Chaos, gravity, and quantum physics all work together to keep information flowing freely in the world. The Bekenstein bound is the final limit on not only what we can access, but also what can exist. The heat-death horizon, when the universe runs out of energy. It's not just what we can measure that holds us back. Going forward, the universe will let it happen, because everything stops in the end. In the farthest, coldest parts of time, this end is known as heat death. This is not the dramatic blast of a dying star or the loud crunch of the universe falling. It's the slowest, quietest fade-out you can think of, a whisper in the sky that goes on forever. And it's scarier than any end-of-the-world blaze. Heat death is what happens when all the usable energy in the universe runs out. When every star has burned its last atom of hydrogen. When every black hole has evaporated into Hawking radiation. When every molecule has settled into a lukewarm fog of statistical nothingness. It is the most chaotic state possible, and no work can be done there. There are no systems, no life, and no processing of information. Nothing but silence. The thought comes from the study of heat and cold. The measure of chaos, entropy, always goes up in a closed system. And this trend can't be stopped if the universe is a closed system, which is what most cosmic models say it is. It takes a very long time for everything to end. This is important because even if we could observe everything, even if we built computers the size of solar systems and mastered every physical law, we'd still hit a hard wall. Because at some point, the universe simply stops providing. There will be no more energy gradients to exploit. No difference in temperature. No flow of time, at least not in any meaningful sense. The most important thing to remember is that knowledge needs energy. Bits change from 0 to 1 to make computers work. That takes strength. Putting away memory, power. How do computers talk to each other? Power. The universe can't be in thermodynamic equilibrium for anything to be possible, not even thought. So when the universe reaches heat death, it's not just that stars disappear, it's that everything else goes with them. Knowledge becomes impossible. Computation becomes impossible. Even time, that ever-ticking background, may cease to have any meaning once there's nothing left to change. This isn't pure speculation. Models suggest that galaxies will evaporate over 10 circumflex 19 to 10 circumflex 100 years, depending on the timescale. Black holes take longer, much longer. But even they die eventually, via Hawking radiation, a process that transforms their mass into a trickle of thermal light. What's left? Small bits mixed together in a dark, watery soup. The universe's last few sparks are too spread out to communicate with each other. If someone is in this place, they can't watch anything, not because they're dead, but because it's physically impossible to observe. And here's the saddest cosmic irony. We still can't beat time, even if we become as smart as gods, catch every photon, and change every atom. The timer runs out. The end of the world is the heat death. This is not because we don't have imagination, but because the universe itself might not be able to support fantasy any longer. The edge of time. Why the beginning may be forever hidden. When we think about time, we like to picture a road that goes both ways. The future seems to go on forever, and the past is like a trail of tracks behind us. When we ask a question that seems so simple, how far back can we really see? That image quickly falls apart when we think about the size of the universe. We can see things with our eyes as well as light, gravity, math, and theory. The truth might make you feel bad. The cosmic microwave background is the oldest light we can see, and it's already given us a wall to hit. But if we go further back into the fog of cosmic history, we find a place that is full of doubt guesswork, and maybe even something worse, permanent ignorance. All known science starts to fall apart at a certain point in the early world. It happened about 105 seconds after the Big Bang and is known as the Planck epoch. That's a trillionth of a second, which is so very short it's hard to understand. Before that, we don't have any math. No types that have been tried, I have no idea. It's not just a limit of tools or measurements, it's also a limit of what people can understand. At these energy levels, our best ideas, general relativity and quantum physics, can't work together. They both want to talk, but they don't speak the same language. Gravity won't quantize, and quantum physics won't bend to the curve of gravity. It gets worse. This isn't just a technology glitch, it's a basic limit. It's called the cosmic singularity, but it might not be real. It's where the bends in space-time are so sharp that all lengths get smaller and time stops being useful. Some theories suggest the universe had no beginning, only a bounce from a previous collapse. Others propose time itself is emergent, and that before the Big Bang is as nonsensical as asking what's north of the North Pole. Still others, like certain string theories, postulate pre-Big Bang universes stretching eternally in either direction. But here's the rub. We may never know which is true. Why? Because we're trapped inside this particular expansion of space and time, and we can't rewind the film beyond the first frame. Every signal, every particle, every relic we can detect comes from after that moment. There is no fossil record of the singularity, no buried evidence of whatever kicked off our cosmic clock. It is famously hard to find even theoretical tools, like the idea of gravitational waves from the Big Bang. And even if we did find them, it might not be clear how to understand them. We're not talking about straight views, we're talking about chances and echoes. It's scary to think that the beginning of time could be the most exact limit of all, not a veil we can lift or a puzzle we can figure out, but a limit that is built into the real world. As far as we know, no one can cross that line in our story. The forbidden equation. Why a final theory might be unknowable. Since the beginning of time, unity has been the dream of physics. To use a single beautiful equation to explain all the different laws, like the force of gravity, the dance of electricity, and the quantum jitter of particles. A plan for everything. It's the most important thing in science. What if that equation doesn't exist, though? Even worse, what if we never find out, even if it does? This isn't a failure of imagination. It's a limit baked into logic itself. Enter Gödel's incompleteness theorems, two mathematical revelations that shook the foundations of knowledge. Gödel proved that any sufficiently complex mathematical system will contain true statements that cannot be proven within that system. In other words, there are facts that are true but cannot be derived. And if mathematics, the language of physics, has these blind spots, then physics inherits them too. This leads to a scary conclusion. There may be cosmic truths that we can never reach, not because of the tools we have, but because the way logic is set up makes it impossible. We could make ideas, models, and calculations that are better and better, but we would still hit a wall. Physicists already run into this. Quantum mechanics and general relativity are two of the most successful theories ever created. They work flawlessly in their own domains. But when you try to merge them, say in the heart of a black hole or the origin of the Big Bang, they contradict each other. Efforts to unify them into a quantum theory of gravity, like string theory or loop quantum gravity, have been running for decades. And yet, a complete solution still eludes us. It's possible that the world is not naturally able to be unified. What if there isn't a single system that can accurately explain all of nature's layers at the same time? Not because they aren't smart enough, but because reality isn't fully consistent with itself. This echoes the undecidability problems in computer science. Just as there are problems that no algorithm can solve, there may be physical questions that no theory can answer. Not because we haven't found the answer, but because no answer can exist that's both consistent and complete. It changes what final means in science if this is true. It's possible that the theory of everything is also the theory of everything we can reach. A local answer in a fractal universe that works in a small area but never sees the whole picture. Still, this is not a loss. There's style in the hunt. We find out what is possible when we try to do the impossible. When we push the limits of what is true, we change what we know. Not about how great the world is, but about how complicated it is. There is a chance that we will never write the band equation, but we can follow its shadows, feel its weight in our models, and get a glimpse of its shape in the things it does that we still can't explain. The final bit, estimating the universe's maximum information. What if we could only know so much? Not how far we could go or what we could see. The universe is very big but not infinite in the way we usually think of it. It has a limited number of bits, a limited area that can be seen, and most importantly, it can only keep a limited amount of data. One very real thing is that the world can only hold so many facts. And that's it when you reach that number. That's the whole story. Let's try to visualize this. Imagine the universe not as a boundless ocean, but as a massive hard drive. Its memory is determined not by its volume, but by its surface area, a strange result born out of black hole thermodynamics. In short, the more surface area, the more bits you can store. And that limit isn't arbitrary. It's defined by Planck units, the smallest meaningful scales of length and energy. We find something amazing when we apply this idea to the universe we can see. We can guess that the total amount of data that could ever be stored in our visible universe is about 10 plus bits by splitting the surface area of the cosmic horizon into units of the Planck scale. There's one there, then 120 zeros. Even though it's unimaginably big, it's important to note that it's not endless. That means that even if we had a perfect copy of the universe, it would only need that many bits to work, in idea at least. This number, though massive, tells us that there is a hard ceiling on discovery. We could map every galaxy, catalogue every particle, calculate every waveform, and one day we could hit the edge of novelty. We'd have all the information the universe contains. After that, the only way to learn something new would be to generate it, through experimentation or interaction. The blank slate would be full. Some of our biggest ideas are also changed by this limit on information. It means that the world can be summed up in a few words. The rules and information inside it can be stored like data. Some scientists even go one step further and say that the universe is a computer. The way it changes is controlled by a formula built into the shape of space-time. It has to do with black holes. In a strange way, they are the best natural ways to store knowledge. Black holes would be the best place for the world to store its secrets if it had to pick. But they don't have a keyboard like ours does. When you put information in, it stays there, maybe forever. When infinity breaks us, the ultimate wall of the multiverse. The idea of true infinity scares people. We might picture something very big, like a desert, an ocean, or a sky full of stars at night. But real infinity is different. It's not just big, it has no edges or bottom, and is deeply contradictory. This is most upsetting when it comes to the idea of the multiverse. To be clear, we don't know if the multiverse exists. Many scientists think it's at least possible, though. So if it does, it could mean that we have learned everything there is to know. This is the idea. The world is like a foam that is always growing bigger and bigger. Each bubble follows its own set of physical rules and has its own mix of matter and energy. It also has its own start point and maybe no end point. There are universes that don't last long. Some are weird. Some are almost the same as ours. In an infinite multiverse, every possible configuration of particles will occur. Not just once, but an infinite number of times. That includes an infinite number of you. Some that made different life choices, some that never existed, some that are watching this video in a universe eerily similar but slightly off. It also includes universes with no stars, universes where gravity repels, universes with no time at all. That's the measure problem in multiverse theory. How do you meaningfully compare infinities? If there are infinite copies of everything, What does it even mean to say something is likely? If 99% of universes are empty, but 1% teem with life, and both sets are infinite, what's the probability of finding ourselves in either? The math gives no answer, because infinity breaks the rules of probability. There is a problem of knowledge here. How would we know anything useful about the world as a whole if we could see other universes, which we can't do right now? Every measurement we make is a drop in a sea that never ends. Even worse, it means we will never know if our world is unique or normal. In other words, the multiverse is more than just a distance limit. It's the edge of truth. It breaks down the tools we use to understand. The things that help us control atoms and walk on the moon don't work when we look at the endless. Even if a future superintelligence could travel between universes, catalog them, and decipher their physics, it would still be working with incomplete data. Always. Forever. There will always be more beyond the horizon. More variations. More contradictions. More answers that lead only to more questions. Some physicists, like Max Tegmark, have leaned into this, classifying all mathematically consistent universes as equally real. Others urge caution, warning that if a theory predicts everything, it predicts nothing. But whether you embrace or reject the multiverse, its implications are clear. A place where knowledge does not end, but becomes unreachable. Not because we lack intelligence or tools or time, but because some answers are drowned in an eternal infinity of noise. And so, after 13.8 billion years of cosmic unfolding, after millennia of observation and equations, after string theory, gravitational waves, and AI-assisted discovery, a spot where information doesn't end, but can't be reached. Not because we aren't smart enough, don't have the right tools, or don't have enough time. It's because some answers are lost in a never-ending stream of noise. In the end, after 13.8 billion years of cosmic unfolding, thousands of years of observation and math, string theory, gravitational waves, and AI-assisted finding, we are left with this terrifying truth. The cosmic neutrino background, the faintest echo of the Big Bang. We've seen the light from the beginning of time. A weak microwave hiss can be heard across the sky. It's called the cosmic microwave background, CMB, and it's the glow left over from the Big Bang. However, what if there is another background, an even older and weaker signal that has been speaking to us since the beginning of time? Yes, there is. The cosmic neutrino background, CVB, is the name of it. Back then, the universe was still hot and dense, but just cool enough for neutrinos to decouple from matter and fly free. Ever since, they've been traveling through space, unaffected by magnetic fields, almost unscathed by matter. They've been on a 13.8 billion year journey, silently echoing the moment our universe began to expand in earnest. Unlike the CMB, though, we've never directly detected these relic neutrinos. They're too low in energy. The CMB photons we detect today have cooled to 2.7 Kelvin, but the cosmic neutrinos, their temperature is predicted to be around 1.95 Kelvin, even colder, even harder to find, and their energy is so low that current detectors can't pick them up. It's not that we haven't tried. Scientists have thought of ways to catch them, such as using very uncommon interactions, such as neutrinos capturing nuclei that are decomposing beta particles. A project called Ptolemy is meant to do just that. But even in the best case, it might only find a few events a year, if we're lucky. This brings up a scary thought. We might never find them at all. As the universe continues to expand, these primordial neutrinos are redshifting, losing energy with every passing eon. Eventually, they may become undetectable, not because they vanish, but because they'll fall below the energy threshold of any conceivable detector. They'll blend into the fabric of space itself, unreachable forever. These neutrinos could reveal secrets about the first second of the universe, a time before light, before atoms, before galaxies. They could offer clues about the number of neutrino species, their masses, or even exotic interactions that shaped the early cosmos. And perhaps most tantalizing of all, they might hold fingerprints of physics beyond the standard model, including sterile neutrinos, dark matter interactions, or hints of cosmic inflation. But it gets harder to hear them every second. The CVB isn't just a space junk in this way. It's time to go, a signal that goes away. One last word from a time we will never see again. We might lose it forever if we don't quickly find a way to find it. For many people, it will just be another imaginary ghost that they can guess about, but never really understand. That's the main idea that keeps coming up on this trip. Not just limits of the body, not just ones that are observational, but there are limits that show where time, energy, and knowledge end. It's possible that the cosmic neutrino background is the last word from the start of everything. It's going away quickly. The more we learn about the world, the more we understand that we will never be able to reach all of it. Quantum noise, redshift, entropy, or even the structure of space-time itself can hide whole layers of reality. It's not just faraway galaxies that are going beyond the cosmic horizon. At first we thought we knew everything, but now we see that the universe is full of things we can't do, places we can't go, and problems that may never have answers. But that shouldn't make you sad. It should make you wonder. As long as there are limits, there is still wonder. And wonder where new things are found. Don't forget to like, share, and follow if this trip into the edges of reality made you curious, made you question what you thought you knew, or gave you a new way to think about the universe. Maybe the next big idea is just around the corner, just like the edge of the world.